Okay, so in this video, I am going to show you two examples of how to solve word problems using differential equations. The first one involves Newton's law of cooling, which states that the rate at which the temperature of an object changes is going to be directly proportional to the difference between the temperature of the object and that of the surrounding medium. And before I set the differential equation for this problem, I am going to finish looking at the information that I have. So I have that the horseshoe is heated to a temperature of 100 degrees Celsius and then immersed into a large tank of water, which has a temperature of 30 degrees. The temperature is considered constant at time 0. And then after 3 minutes, the temperature has been reduced to 70 degrees. The first thing that we're going to do here, that we're asked to do, is to derive an expression that gives the temperature at any given time. So that means that we're going to have to solve the differential equation and find the function for the temperature. So the first thing I'm going to do is to call T, capital T, is going to be the temperature of the horseshoe, temperature at time T, and T over here is going to be expressed in minutes because we have this expression over here that says minutes, so this is going to be in minutes. And this is useful in case the question over here changes the unit afterward. In this case, it doesn't seem like it's going to be the case, but it's always useful to state what the units are going to be in these cases. All right, so Newton's law of cooling states that the rate at which, so we know that whenever we have a statement that refers to the rate at which something is changing, we're talking about the derivative, right? So rate at which the temperature of an object changes means the derivative of the temperature with respect to time. Then we have that is going to be proportional. So this is proportional, means we're going to have to include a constant of proportionality on the right-hand side. So here we're going to have is equal to some constant times whatever this is going to be proportional to. So, and this here says that this is proportional to the difference meaning minus, between the temperature of the object and that of the surrounding medium. So that means this is going to be proportional to the difference minus of the difference between the temperature of the object, so between the temperature of the object and that of the surrounding medium. So I'm going to put S for surrounding. We're going to change that pretty soon. Now, when we say difference, in this case, it doesn't really matter whether we put S minus T or T minus S, because all that that's going to affect is the value that we will then find for the constant K over here. Because this constant we're still going to have to find if you choose the opposite order for S and T. The only thing that will change is that the value of K that you will find is going to be minus whatever value I find in this expression. But both of the formulations are correct. Now, I know that the temperature of the surrounding medium is 30 degrees, at least in this case. So the surrounding medium is at 30 degrees. And so I'm going to have that this is the temperature, the derivative of the temperature is going to be equal to K times temperature of the surrounding medium, 30, minus the current temperature. Okay. Then I also have a couple of initial conditions. I'm going to write those down right away so that we don't forget about them after. I know that the temperature, the initial temperature, is equal to 100. So initially, the temperature is equal to 100 over here. And after 3 minutes, the temperature has gotten to 70 degrees. So T of 3 is going to be equal to 70. Okay, so this is all the information that we have, and that is going to help us solve this problem. So what I have is first a differential equation, and as usual, I'm going to start by finding the general solution to the differential equation, and then I'm going to use that general solution in order to find the particular solution using the initial conditions. So the first thing is solving the differential equation. I have dt over dt, d capital T over dt is equal to K times 30 minus T. And our strategy in these cases is always to try to find everything in terms of one variable on one side and everything in terms of the other variable in the other side, so that I can independently integrate the left-hand side and the right-hand side. So what I'm going to do here is divide both sides by 30 minus t and multiply both sides by dt. Right? So if I divide both sides by 30 minus t, I'm going to get dt. Here, this is going to be 1 over 30 minus t. And on the right-hand side, I'm going to have still k, that hasn't gone anywhere, and then times dt. Which means that to find the value of t, I'm going to have to evaluate the integral of 1 over 30 minus t d capital T. And that is going to be equal to the integral of k times d lowercase t. Okay, so on the left-hand side, I have 1 over some function, which is just a linear function. So I'm going to go right ahead and conclude that the antiderivative of that is going to be ln of 30 minus t. But because the constant that is multiplying the value of t over here is minus 1, so this is not just 1 over t, it's ln of 1 of a constant minus t, then I have to divide by that. So I'm going to get ln of 30 minus t divided by -1. And if you're still struggling a little bit with that, you can go ahead and do a full substitution in order to get this, but you should always get the antiderivative of 1 over 30 minus t is going to be ln of 30 minus t divided by -1. I could also add a constant over here, but because I'm going to add a constant on the right-hand side, there's no point in adding a constant on each of the sides because eventually I'm going to end up combining those two constants anyway. So I'm just going to add the constant of integration to the right-hand side, and I'm going to get that that's k times t plus some constant t. Okay, so now I have integrated both sides. This was not too difficult. What I'm going to have to do now is to now solve for t, right? So what I'm trying to find is the temperature as a function of time, which means that I'm going to try to find t as a function of lowercase t. The first thing is I'm going to multiply both sides by -1, which will give me that ln of 30 minus t is equal to minus k times t minus c. And this is by just distributing the -1 right away. Then we're going to have to isolate the value of capital T, but that is inside a logarithm. And so if I want to get the inside of the logarithm, I know that I'll have to put both the left-hand side and the right-hand side on the exponent of e. So I'm going to have e to the power of ln 30 minus t, capital T. And this is going to be equal to e to the power of minus k times t minus c. On the left-hand side, this is fairly easy. I'll get 30 minus t because I have that e to the power of ln of something. Because they're inverse functions, these two cancel each other out. And so I get that 30 minus t is equal to e to the minus k times t. And I'm going to write this as e to the minus k times t and times e to the minus c, right? So because there's a sum over here at the exponent, that's the same as a product if I separate those two exponents. And here, I am going to write this down as a brand new constant because I know that the value of c is arbitrary, which means that e to the power of minus c could also be any value, which I'm just going to denote in this case by d. From here, I get that 30 minus capital T is equal to d times e to the minus k times t. And because I'm trying to solve for t, I am going to subtract d e to the minus kt on both sides and add t on both sides. So I get here 30 minus d e to the minus k times t. And this is going to be equal to t. All right, so now we have a general solution. Let me write that down again. So temperature is 30 minus D e to the minus k times T. And all that I have to find now is the values for the constant D and the constant K. All right, so here we go. There. At this point, I'm going to start using my initial conditions. So I have found the general solution to the differential equation. I am going to now use the initial conditions that I was given in order to find the two things that I still don't have values for in my equation, which are D and K. So first, let me set T of 0 is equal to 100. So I'm going to make this equation true by first plugging in 0 into my expression for the temperature and then setting that equal to 100. So that means that 30 minus D e to the minus k times T, sorry, not k times D, k times 0, k times 0, this is going to be T of 0, and this is equal to 30 minus D times e to the 0, which is the same as 30 minus D. And so what I have is that 30 minus D is equal to T of 0, and T of 0 is also equal to 100, which means that 30 minus D is equal to 100. So if I set that equation, I get 30 minus D is equal to 100, which means that D has to be equal to negative 70. Right? So from here, I have now a new piece of information, which is D is equal to negative 70. And that means that the temperature is actually given by 30 plus 70 e to the minus k times T. So why plus 70? Because this is minus minus 70, which ends up becoming plus 70. So that's using the first initial condition. Now we're going to use the second condition that we're given, which is that T of 3 is equal to 70, which tells me that if I replace 3 in the expression that I have for the temperature, I will get the value 70 over here. So that means 30 plus 70 times e to the minus 3 times k is going to be equal to 70. Right? So I've replaced just t over here. And from here, I'm going to solve for the value of k. So this tells me that 70 e to the power of minus 3 times k is going to be equal to 70 minus 30, which is 40, which means that e to the power of minus 3k, if I divide both sides by 70, is going to give me 40 divided by 70, which is the same as 4 divided by 7. This means that I'm going to have minus 3k be equal to, and in the same way that all the way over here, when we wanted to solve for the inside of a logarithm, we had to put everything on the exponent of e. Over here, if we're trying to find the exponent of e, then that means we're taking the logarithm on both sides. So minus 3 times k is equal to ln of 4 over 7. Which means that k is equal to minus ln of 4 over 7 divided by 3. Okay, so now I can actually replace this into my expression for t. So let me just make myself some space over here. There you go. And I'm going to have that. Because I know that my expression is of the form t is equal to e to the power, to 30 plus 70 times e to the power of minus kt. So this is e to the power of minus k, which is minus times minus ln of 7. So minus times minus ln of 4/7 divided by 3 times t. I can cancel these minuses because minus minus is going to give plus, and this is 30 plus 70 times e to the ln of 4/7 times t/3. And the reason that I want to write this as e to the ln of something times another term is that I know that the exponentials and logarithms are inverse functions. So that means that I'm going to be able to simplify these two as long as I'm able to just get a term that is e to the power of ln of something. So from here I can rewrite this as 30 plus 70 times e to the ln of 4/7. And we know that when there's a product in the exponent of something, that's like first applying one of the terms and then applying the second term to the result. So that means I'm going to get e to the ln of 4/7, the whole thing to the power of t/3, which gives 30 plus 70 times 4/7 to the t/3. And this is the final expression that I have for the temperature as a function of time. So this is the answer for this problem. Here we go. Now, at this point, I have found the value of, the expression for the temperature as a function of time. That's question A. For B, they're just asking me to evaluate the temperature at a specific time, which is t is equal to 5. And so I'm just going to have to plug in the time, 5 minutes, so t is equal to 5, into the expression that I found for the temperature. So t of 5 is equal to 30 plus 70 times 4/7 to the power of 5/3. By plugging this in your calculator, you will get a result that will be approximately 57.54, which means that after 5 minutes, the temperature of the horseshoe will be 57.54 degrees Celsius. Temperature is 57.54 degrees. And that's all problem, the whole problem. So in the first case, we just found the expression for the temperature, whereas in the second question, we actually found the temperature at a given time. Okay, so this is example number 1. In example number 2, I'm going to go ahead and use one of the most complicated examples that we're going to see in this class, which is what we talked about in the first class on differential equations, which was a restricted growth. Okay? So here we go. We have that a biologist has determined that the maximum number of fruit flies that can be sustained in a carefully controlled environment is m equals to 400. Then the rate at which, okay, so that should be an indicator that that's when we start paying attention quite a bit, right? So the rate at which the population grows, that already means derivative. I'm going to start by first writing P seems to be the thing that I'm looking at. So the rate at which the population grows. So P is the thing that I'm going to look at, which is going to be the population at time t. And then this is jointly proportional. So the rate at which the population grows, that's dP over dt, is jointly proportional. Jointly proportional means it's proportional to two things. First is the difference, to the current fruit fly population, so current fruit fly population, and to the difference between the maximum population, 400, and the current population. That means that I'm going to need to include two terms here. I'll have one term that will be the current fruit fly population, so that's the current population, and the other term is the difference between the maximum 400 and the current population. So here I'm going to write that as 400 minus P. I'll specify that again right now. Even if you write this as P minus 400, it doesn't matter the order in which you write this. The only thing that will change after that is whether you find a value of K that is positive or negative. All right, so I've set up my differential equation. And now I can try to figure out how to write my, my conditions. So I have that the initial population is 10, so that means P of 0 is 10, is equal to 10. And the population has grown to 45 after 10 days. So population after 10 days is equal to 45. Here I forgot to specify, but time is expressed in days. And the question is what the population will be after 20 days. So what is P of 20 going to be? Okay, so we can start by solving the differential equation, and as usual, then we'll use the conditions that we were given in order to find the constants that will inevitably appear once we find the general solution. So I have the differential equation dP over dt is equal to K times P times 400 minus P, which if I separate will give me the dP over P times 400 minus P is equal to K times dt. Right, so I have dP over P times 400 minus P is equal to K times dt, and then I'll be able to integrate both sides separately. So I'll have integral, this thing over here is going to be the same as 1 over P times 400 minus P times dP. And on the other side, I'll have the integral of K times dt. Okay. All right, so the right-hand side is not really that difficult to evaluate, but the thing that might be a little bit trickier is to evaluate the integral of the left-hand side. So I'm going to focus on that, and then I'll just plug in whatever expression I find for that left-hand side into the equation that I have. So let me, for now, just focus on the left-hand side over here. So I have to evaluate the integral of 1 over P times 400 minus P, which means I have a polynomial that is already factored at the denominator, and at the top I have nothing that will help me do, for example, a substitution using that denominator. So what this suggests is that I have two factors of the denominator, which I could then write, hopefully, as 1 over, so I could probably write 1 over P times 400 minus P as something divided by P plus something else divided by 400 minus P. Right? And we know that because if we try to combine these two fractions, we're going to end up multiplying the denominators, and so we'll get the same denominator as the left-hand side. The only thing that might change over here that might be tricky is to find the values of a and b, but we already know how to do that. This is a classic partial fractions problem. Okay, so what we'll do is first put the right-hand side on the same denominator and then find the values of a and b. So this is going to be a times 400 minus p plus b times p. And the whole thing will be on the same denominator, which is now going to be p times 400 minus p. And this, of course, we want to make equal to 1 over 400 over p times 400 minus p. All right, so if I choose values on the right, so I know that this equation has to be true regardless of what the value of p is. So I want this to be true no matter what the value of my variable p is going to be, which means I can choose specific values of p, and then I can force the equation to be true. If I have p is equal to 0, then the left-hand side will still be equal to 1, and the right-hand side will be 400 times a. Right, because b times p will cancel out, so this will be 0, and 400 minus p will just be 400. And that means that a is equal to 1 over 400. And in the same way, if I have that p is equal to 400, then the first term is going to cancel. So the left-hand side will still be equal to 1. And the right-hand side will be 400 minus 400. So that's 0 times a, which is 0, plus 400 times b, which tells me that b is equal to 1 over 400. Now, just as a reminder, you only have to compare the numerators over here because we have specifically made our denominators be the same as one another. So that means that these expressions are going to be the same as long as just the numerators are the same. Okay, so if I go back to the integral that I'm trying to evaluate here, that means that I'm going to end up evaluating the integral of 1 over p times 400 minus p, so this over here, which is equal to this type of expression as long as both a and b are equal to 1 over 400. So this is 1 over 400 divided by p, so that's a over p, plus 1 over 400, which is b, over 400 minus p. dp. And as I said, this was just for me to rewrite the left-hand side so that it would be easier to integrate. But the right-hand side is still the same integral that we were trying to evaluate originally, a times dt. So on the left-hand side, I'm going to start by factoring the 1 over 400 right out of the integral because this is a factor of both of my terms. I'll have 1 over 400, and then the integral of 1 over p plus 1 over 400 minus p with respect to p. And on the right-hand side, I can integrate that right away. This is going to be just k times t, and I'll add my constant of integration. To not have to worry about the, this 400 right now, I'm going to multiply it over right away. So I'll multiply it on both sides. And I'll have 400 times kt plus c. And on the left-hand side, what I'm going to do is to integrate each of these pieces separately. So I'll have ln of p, an absolute value, plus ln of 400 minus p. But here we are in the same situation as in the previous problem, which is that the constant that is multiplying the p over here is -1, so I'm going to have to divide by -1 as well. Right? And again, if this is still not intuitive to you, then you can separate this into two different integrals and then evaluate the integral for this term by using substitution. So I'll simplify this a little bit just to make it look nicer, because we're going to have to do to find p anyway. So we would like to write this in an easier way. So I have ln of p minus ln of 400 minus p. And on the right-hand side, I'm going to have 400 times kt, and I'm going to distribute that right away. Now, the idea over here is still to be able to solve for p, right? Because I'm trying to find the function p in terms of time t. So I'm trying to find the population at time t, which means p is a function of t. Which means I'm going to have to get rid of the logarithms that I have on the left-hand side over here if I want to solve for that value of p. Lucky for us, if we use the laws of logarithms, we know that logarithm of something minus logarithm of something else is the same as taking the logarithm. So here, just let me write this. We're trying to find p. This is our idea. And so on the left-hand side, we're going to use the laws of logarithms to write this as ln of p divided by 400 minus p. And on the right-hand side, I have still 400 kt plus 400 c. But you see now, because this is just one logarithm, I know that if I put everything on the exponent of e, I'll be able to get rid of this logarithm, and then I'll just have to find, I'll just have an expression on the right-hand side that is written in terms of t. So I have, by taking this to the power of e, I have p over 400 minus p, and on the right-hand side, I now have 400, e to the 400k times t plus 400 times c. And now, because I'm going to be solving for p and I'm going to be manipulating the term that is on the right over here, I'm going to actually try to write this in a nicer way. So I'm going to split the two exponents, and I get this is the same as e to the power of 400 kt times e to the 400 c. And here we're going to do a little bit more with this. So again, I'm trying to solve for p, so that means I'm going to have to play with the terms on the left and the right-hand side. So all of this, like e to the 400c and e to the 400kt, they seem like they're going to be a bit messier to deal with. So instead, I'm going to write e to the 400c, because the value of c is arbitrary and I'm just trying to find that value. I'm going to write this as some other constant d. And I'm going to do the same exact thing with 400 times k. Right, so here I have 400 times k. Well, I'm trying to find the value of k, but if I just label 400k as something else, then I am going to find something that is going to be that I'm going to be able to use regardless, right? So maybe I'm going to call this lowercase a. All right, so if I write my equation again, I'm going to have p over 400 minus p is equal to d times e to the a times t. Now, if it's not intuitive for you why I can replace this by a and d, remember that you can still solve everything by writing this as e to the 400 kt times e to the 400c. It's just that it's going to be messier. You're going to have to be dealing with more writing, and so I'm just trying to make it a little bit more practical. So now I'm going to try to solve for p. Okay, at this point, this is the only thing that I have left to do. And to solve for p, I'll start by multiplying over 400 minus p over here, right? Because I'm trying to find p on each side. So I'm trying to isolate p, which means putting p on one side and everything else on the other side. But right now, this 400 minus p at the denominator is bugging me. So if I multiply it out, I know at least that I will be able to distribute it. So I'll have d e to the at times 400 minus p. And what I'll do is still keep the left-hand side the same way, but now I'm going to multiply out the d times e to the at times 400 minus d e to the at times p. Right? And now I have p in this term, p in this term, so I'm going to put both of those on the same side. And I'll get the following: p plus d times e to the at times p by adding it on both sides. And on the right-hand side, I still have just 400 times d e to the at. We're almost there. Over here, if I want to solve for p, well, I'm going to try to divide by what's multiplying p, but I have two terms that are multiplying p, which means that I'm going to start by factoring p out. So I'll have p times 1 plus d e a t, which is equal to 400 d e to the a times t. And finally, this means that p times 1, oops, no, the whole point was to divide. So I'll divide by 1 plus d e to the at, and I get that this is equal to 400 d e to the at divided by 1 plus d e to the at. All right, and now we have an expression for p. So let me just make some space to be able to solve the rest of the problem. I have found an expression for p of t. And all that I have to do now is find the values of a and d. Okay, so here is what I have. So where am I? There you go. So I have that p is equal to 400 times d e to the a times t divided by 1 plus d e to the at. Now here you're going to hate me because I'm going to change the names once again, but you see I have d e to the at that occurs a lot in the expression that I have over here, right? So I have one at the top and one at the bottom. So what I'll do now, and this will simplify life a little bit afterward, is to divide both the numerator and the denominator by d e to the at, right? So I'll have, this is divided by d e to the at. It's going to give us a nicer expression, but as usual, if you keep it as is, you'll find the same function. It's just going to be written probably slightly different. So at the numerator, I find 400, and at the denominator, I'll have 1 over d e to the at plus 1. You're going to say, okay, so what's the point of doing this? This looks more complicated, but if I write now 400 over here, I'll still have my plus 1 there. This is the same as writing 1 over d times e to the minus at, right? Because e to the at at the denominator of an expression is the same as e to the minus at, and I can rename 1 over d some other letter. So I can just write that term over here maybe as, I don't know, what letter could we use? We can use capital K. Okay, so it doesn't matter which letter you use, it's just a matter of labels. It's all about the labels here. So finally, we have an expression for P, which is P of T. The population at times T is given by 400 over K e to the minus a times t plus 1. And right now, I actually only have one thing left to do, which is to find the values of my constants, which in this case I have renamed capital K and lowercase a. So I'll use my different conditions that I have. I start with using the fact that P of 0 is equal to 10, which means that if I plug in 0 to my expression, so P of 0, I'm going to get 400 divided by K, capital K, times e to the power of 0 plus 1. And this is the same because e to the power of 0 is just equal to 1. This is 400 over capital K plus 1. Now, this is equal to 10 because I know that the population at time 0 is equal to 10, and this gives me the population at time 0. This is equal to 10. Now, if 400 divided by something is equal to 10, then that means that that something has to be equal to 40. Oops, that something means K plus 1, not K. K plus 1, the denominator, has to be equal to 40, which in the end means that capital K over here is equal to 39. And from here, I get now that this is P of T is equal to 400 divided by 39 e to the minus a t plus 1. And I now have also that P of 10 is equal to 45. I can plug in 10, and I will get that P of 10 is equal to 400 over 39 e to the minus a times 10, so minus 10a plus 1. This is an a. And this is equal to 45. Now, if I divide both sides by 45, multiply both sides by 39, I get that 400 over 45 is equal to 39 e to the 10a e to the minus 10a plus 1, which means that 80 over 9 is equal to 39 e to the minus 10a plus 1. Now, if I solve for a, I'm going to get 80 over 9 minus 1, which is 71 over 9 is equal to 39 e to the minus 10a, which means that 71 divided by 9 times 39, so 71 over 351 is equal to e to the minus 10a. And this when you get that minus 10a is going to be equal to ln of 71 over 351, which once you divide by minus 10 is going to be this divided by 10. Okay, almost done. Almost done. And I've said that a couple of times, but it's really it. Now we just have to simplify the expression for the population and then evaluate the population after 10 days. So my population is P is equal to 400 divided by 39 e to the minus a, so e to the minus this, which is minus means ln of 71 over 351 times t over 10 plus 1, which is equal to 400 over 39. And this is the same as e to the ln of 71 over 351 times t over 10 is the same as if I just evaluated this and then put everything to the exponent of 10. So this is times 71 over 351 to the power of t over 10 plus 1. And so if I want to evaluate this as 20, I now just have to plug in the value of 20. So this is the expression for any value of t, p as a function of t, and now I just have to plug in 20, which means I'll have 400 over 39 times 71 over 351 to the power of 20 over 10, the whole thing plus 1. Which after you plug into your calculator is 154.09, 097.1, which means that after 20 days, there will be 154 fruit flies. Okay. All right. So again, this is one of the most difficult type of problems that you would encounter. And if you were to find something like this, I would guide you through the different steps that you need to solve. But one thing that you will not be able to get away from in this section about solving problems using differential equations is to solve equations that involve exponentials and logarithms. So if that's still something that you're struggling with, now's the time to review it and really work on problems that involve this type of equation. You're not going to be able to get away from it. So it's really going to be a good investment of your time.